Hello, this will be a demonstration of proposition 14 from book 6 of Euclid's Elements, which says that in equal and equiangular parallelograms, the sides about the equal angles are reciprocally proportional, and the converse, equiangular parallelograms in which the sides about the equal angles are reciprocally proportional are equal to one another. I should say that that's actually a partial converse and not a total converse. What we're given is two parallelograms AB and BC, which have equal angles around B. So that's going to look like this. Now some parallelogram AB, and then some other parallelogram BC. That. And we're going to place the two straight lines, DB and BE, in a straight line with one another, from which it follows that the two straight lines FB and BG will also be in a straight line with one another. The proof of that goes something like this. We know that the angle FBD is equal to the angle EBG, which means that if we add the angle EBF to both by common notion 2, we will get equals as well. So the angle DBF plus the angle FBE is equal to the angle EBG plus the angle FBE. But we know by proposition 113 that if a straight line falls upon straight lines, the adjacent angles shall add up to two right angles. So the angle DBF plus the angle FBE is equal to two right angles, which means by common notion 1 that the angles EBG plus FBE also add up to two right angles, but adjacent angles, if the adjacent angles adding up to two right angles, we can say by proposition 114 that if you have a straight line falling upon two straight lines such that the adjacent angles add up to two right angles, the two straight lines shall be in a straight line with one another. And so the angles EBF plus EBG adding up to two right angles, we can say that because DB is in a straight line with BE, FB is in a straight line with BG. Now, in the first case, the parallelogram AB is going to be equal to the parallelogram BC, from which we shall prove that the sides about the equal angles are reciprocally proportional. And what that's going to look like is that DB is to BE, just as BG is to BF. Reciprocal proportionality, if we were to define it like proportionality in the book 5 definitions, would be if you have four magnitudes and the first is to the second just as the fourth is to the third. Normal proportionality would be the first is to the second just as the third is to the fourth, but reciprocal, the first is to the second just as the fourth is to the third. And when it comes to parallelograms, the way to be tipped off by this is that you have two sides from the same parallelogram next to each other. So we know that DB to BE, just as GB is to BF, is reciprocal proportionality because we have the two sides BE and GB of the same parallelogram BC next to each other. And so, given that the angles about B are equal to each other and that the parallelogram AB is equal to the parallelogram BC, we're going to prove that DB is to BE just as GB is to BF. But if on the converse, we are given that GB is to BF just as DB is to BE, and again the angles about B being equal, we're going to prove that the parallelogram AB is equal to the parallelogram BC. We're going to begin with the first case, where we're given that the two parallelograms AB and BC are equal to each other. And this being the case, we're going to finish the parallelogram FE. This is just going to be by postulate 2, so we're going to produce a F 2.H. And we're also going to produce CE 2.H, so we're going to have the whole parallelogram FE like that. Now, having been given that the parallelogram AB is equal to the parallelogram BC, we can say by proposition 5.7 that equal magnitudes have the same ratio to the same, and so we can say that AB is to FE just as BC is to FE. But we notice that the parallelogram AB and the parallelogram FE are under the same height, which means by proposition 6.1 they are to each other as their bases. So the parallelogram AB is to the parallelogram FE, just as the base DB is to the base BE. And similarly, because the two parallelograms BC and FE are also under the same height, they are to each other as their bases, again by proposition 6.1. So the parallelogram BC is going to be to the parallelogram FE, just as GB is to BF, which then means by proposition 5.11 that ratios which are the same with the same ratio are the same with one another. We can substitute these two ratios, DB to BE and GB to BF, into our original proportion that the parallelogram AB is to the parallelogram FE, just as the parallelogram BC is to the parallelogram FE, which means that DB shall be to BE, just as GB is to BF. And this is what we wanted to prove. Given that the angles about B are equal and that the parallelogram AB is equal to the parallelogram BC, we wanted to prove that the sides about the equal angles are reciprocally proportional, namely that DB is to BE just as GB is to BF. And this is exactly what we have proven, so we're done with the first case. Now the second case is where we are given that GB is to BF just as DB is to BE. And again, the angles about B are equal. And so again, we're going to complete the parallelogram FE by postulate 2. And we're going to again observe that DB is to BE, just as the parallelogram AB is to the parallelogram FE, again by proposition 6.1, because these two parallelograms AB and FE are under the same height, which means they are to each other as their bases. So DB is going to be to BE, just as the parallelogram AB is to the parallelogram FE. And likewise, the base GB is to the base BF, just as the parallelogram BC is to the parallelogram EF, again by 6.1, because these two parallelograms BE and FE are under the same height, which means they are to each other as their bases. And having been given in the second case that DB is to BE, just as GB is to BF, we can again say by proposition 5.11, we can substitute these ratios in, so that we'll say that the parallelogram AB is to the parallelogram FE, just as the parallelogram BC is to the parallelogram FE. But magnitudes which have the same ratio to the same are equal to each other. That's proposition 5.9. And so we can say that the parallelogram AB is equal to the parallelogram BC. And this is also what we wanted to prove in the second case. Given that the angles about B are equal and that GB is to BF, just as DB is to BE, we set out to prove that the parallelogram AB is equal to the parallelogram BC, and we have just shown that to be the case, which means we are done with the proposition entirely, therefore, etc., Q, E, D. I've got nothing to say about this proposition, so I will end the video here and move on to 6.15.